Alright, Mr. Kwang here. I'm just going to go through question 8 and question 9 for you. So question 8, we're going to talk about double slit experiment. Okay, so I'm going to highlight some key terms for you. Okay, double slit experiment, the slits are 0.2 mm apart and then place 1 meter from a screen. Okay, the light incident has a wavelength of 5.5 times 10 power negative 7 meters. Calculate the linear and angular separation between the second and third bright fringes on the same side of the principal axis. Okay, so there are a lot of key terms. So let's quickly sketch a diagram to help us understand what's going on. Okay, so we have our slit here. Let's just quickly draw this up this way, and then the screen is here. So if we draw our central bright fringe, it looks like this. This is the point where they meet right at the center here, right? So we usually call this point O, right? Okay, then of course if you have so I like to call this C1, first constructive, then second constructive, and then third constructive. Okay, so this is what you have. Let me zoom in a little bit for you guys. Right, so you have, let me just draw another color here. So you have, what you have is this one. You want to find out what's the angle between C2 and C3. What's the difference in this angle? Okay, so first thing first, you need to work out what is this distance here. This is your usually labeled as Y here, right? Right. Then you want to find out the angle. So the angle is this. That is of course your theta 2 and then your theta 3. Okay, so you're supposed to find the difference between two of them. Okay, so for this you can just apply the formula directly in both cases. Alright, so let me just switch to something first. Okay, so we can work out what is our x. Okay, usually, okay, I mix up. The formula usually uses x. We just use x for consistency here. Right, so to find the linear spacing, right, we can just use our formula directly for interference. For two-slit interference, we can do lambda equals to ax over d. Okay, we're supposed to find d. Okay, we're supposed to find x. Okay, so lambda is a wavelength, a is your distance between the slit, x is the fringe separation, d is the distance between the slit and the screen. So just need to make direct substitution for them. Right, so this will be 5.5 times 10 negative 7 equals to a, which is 0.20 millimeters, so that's times 10 negative 3. Okay, find x, okay, divided by distance of 1.00. Alright, did it give 0? Wait, let me check. Just small details. Yeah, 1.00. Okay, then work out x quickly, right? You'll get 2.75 millimeters. Alright, so if you get this, I think I skipped some steps, right? You should have gotten it as 2.75 times 10 negative 3 meters, then you convert it to 2.75 millimeters. Alright, okay, so this is the first one. Next one is supposed to find the angular separation. So you need to work out what is your theta 2, work out theta 3, then find the difference between them. Okay, so this is theta 3 minus theta 2. Okay, so we can use our diffraction grating formula here actually, right? So we're doing, instead of using d sine theta, right, we can use it a sine theta equals to n lambda, where n is either substituted as 2 or n3. Okay, so we need to do it twice. Right, so the first one, let's find for n equals to 2 for the second order constructive interference, right? So this will be, let's sub in the values. This will be 0.20 times 10 negative 3 sine theta 2 is equals to 2 times 5.5 times 10 negative 7. Okay, you work this out, you get theta 2 equals to 0.315 degree. So this is in degree mode. Okay, degree mode on your GC. Okay, then we find for n equals to 3 now. So this is again same working, 0.20 times 10 negative 3 sine theta 3 equals to 3 times 5.5 times 10 negative 7 as well. Okay, alright, and then we do this, you get your theta 3 to be equals to 0.473 degrees. Okay, So your delta theta is equals to 0.473 minus 0.315, which will give you 0.157 degrees. Okay, another way you can do is that, because okay, if you look at your diagram here, okay, if you look at your diagram, right, your 0 is here, your C1 is here, your C2 is here, your C3 is here along the screen. Okay, all this distance is the same. Okay, so basically the angle from the source, right, from the source will be this way. Okay, each angle will be the same as well. Alright, so you can just work out what's the angle, what's theta 1. If you work out theta 1, right, you can basically, this is approximately equals to theta 1, this is also approximately equals to theta 1. Okay, so that's another way of doing this question. Alright, okay, so this is question 8. We move on to question 9 now. Let me just zoom out a bit, go to question 9. Alright, question 9 is a little bit longer, but not too difficult actually. Okay, right now we have this scenario. Let's again highlight terms. We have water waves, alright, water waves, wavelength 2 meters, produced by two generators S1 and S2. So the generators are here, alright, S1 and S2, placed 3 meters apart, alright, and then each generator will operated by itself, produces waves which is assumed to have amplitude of A at P and R. So what it's saying is that by the time this wave from S1 reaches here, or reaches P on its own, right, the wavelength, the amplitude is A. Same way it reaches R, the amplitude is also A, and same for this 2 as well. Right, so they both have, what this is trying to tell you is that both sources have the same amplitude when they come to this point of time, when they come to points P and R on their own. Okay, very important. Okay, then we have some distances. We have this distance is 4 meters and this distance is 3 meters. Alright, so you need to work out the path differences of the waves at P and R. So to work out path differences, right, we need to write down our path itself first. Okay, so for P, let me write it down on the top here. So for P, right, let's write it as, so clearly you can see that S2P is longer than S1P. Alright, and we can work out S2P. S2P, you can use a right angle triangle, so this will be 3 square plus 4 square root, and this is equals to 5.0 meters. All right, 5.0 meters. Okay, so you can see this right angle triangle here, 1 2 3. This is a right angle. All right, so that's S2P. Okay, so your path difference at P, let's just write it as delta x at P is equals to S2P minus S1P, and this will give me 5.0 minus 4.0 and 1.0 meters. Alright, that's for P. Then for R, I think you can see that, okay, if this is R, right, so let's see, so R, this one is here, this is also 1.5, and this one also must be 1.5. Okay, so if we draw the line to R, this is here and this is here, you can see that basically this is an isosceles triangle. So we can quickly see that S1R is equals to S2R. That means your delta x at R is equals to 0 meters. Okay, so that's part 1. Part 2, phase difference. Okay, phase difference, we need to use the phase difference formula. So since we have path difference, right, we can write out the phase difference formula first. So we're trying to find phase difference. We are looking at delta phi is equals to delta x over the wavelength multiplied by 2 pi. Okay, let's box this up. Okay, alright, so let's do for at R. So let's do the phase difference at P first, since the first one. So delta phi at P is equals to the path difference at P, which is 1.0. Wavelength given to us was 2.0 meters. So 2.0 times 2 pi, and this path phase difference is pi radian. Alright. Okay. Then for the next one, delta phi phase difference at R, path difference is 0. 0 divided by 2.0 times 2 pi again, you'll get 0 radian. Alright. Correct. Yeah. R is 0. Okay, then you need to find amplitudes at P and R. Okay, so you can see that right now, for this one, for the first one here, because it's pi radians, right? So this is arriving at, okay, let me write in red color. This is arriving to give you destructive interference. They're arriving out of phase interference, right? Okay, ENCE. Okay, so because this is out of phase, all right. Okay, and then this one is in phase, so this is constructive interference. Okay, so for destructive, right, you can just add them up. Okay, you can just subtract them. Okay, so let me just squeeze it at the side here. All right, so we can work out the wavelength at P. Write it down. So wavelength at P is equals to A plus negative A. All right, and I get 0. And then wavelength at R will be A plus A, and I get 2A. Alright. Okay, so this is for the next one. Alright. Now we move on to intensity of the fine intensity wave. So intensity is proportional to the square of its amplitude. So this is basically telling this I is proportional to A square. Alright. So we're supposed to find first one. First one is, okay, I at P combine. Okay, so I need to subscript it properly, right? So let's call this IP combine over IP single. Okay, so I is 0, right? 0 amplitude. So basically I'm looking for, okay, I'm gonna write, let me find AP combine over AP single, and then I'll square both terms. Okay, so this one I'll get 0 over A whole thing square essentially. So this is 0. Alright. Okay, next we're supposed to find the second one. I think you get the idea. Second one, if you do it, I try to find space to do it. Sorry, it's a bit messy now. You just go squeeze it here. Okay, second one's supposed to find R, right? So this will be IR combine over IR single is equals to AR combine over AR single. You can just square the whole thing outside, that's fine. So this will be 2A over A whole thing square. So I get 4. Right? So these are two answers, and it's all given here as well. Okay. Next, let's look at conservation energy now. So compare the answers in B with reference to the law of conservation energy. Alright, so conservation energy, remember, it applies across physics. So even for here, right, you cannot have more energy than what you have at the start. Okay, so your energy depends on your intensity here, right? So if you look at this one here, right, let's just mark out these 2 points. Okay, so let's say, okay, I'm just going to draw it this way. So P is, sorry. So along this line, P is here, and then R is here. So P, right, is receiving energy of basically 0. Okay, where your intensity is 0. So IP is 0. And then this one here, IR is equals to 4 times. 4 times for the original value. Okay, when there's compared to when there's only one wave incident. Okay, so if you just, this is a quick estimation. If you were to draw a bar chart of this two, right? So if I basically take this value, this is 0, right? And then this value here is basically 4. Okay, if I redistribute this total amount between P and R evenly, right, you will get essentially at P you get 2 and R you get 2. Okay, so if you think about it, right, the total energy is still the same here. Alright, so if you divide it out, right, this each point on average is getting 2 times the original energy, which if you think about it, because right now I have 2 waves that are incoming, right? So I have 2 waves incoming here, over here, right? If you just add them out, right, the energy should just be 2 times of the original. Okay, so if on average is 2, that's fine, because right now this is receiving much more, this is receiving very little, right? But if you redistribute it, they basically get the same amount each. Alright, Yep, so that's it for question 9. You can move on to the rest of the questions as well now. Thank you, bye.